So, we stopped last week, or we will just continue with the stuff from last week, and these were the crystallographic classes. So, when we stopped last week with the tetragonal system, then I will just repeat again the tetragonal system, so that we are getting again on the line. So in the tetragonal system, we have different possibilities. First of all, the a-axis shows the same length like as the b-axis, but it is but c is different. So and then the angles between alpha, beta, and gamma is 90 degrees. Yeah. So we have in this crystal class we have different. We have 7 possible crystallographic classes. We have 4 over m, 4 over m, 2 over m, 2 over m. That means here we have then 4 rotation axis and a mirror axis, and then we have 2 rotation axis in combination with a mirror. Then we have 4 to m that with the line above. That means we have a 4 rotation axis, but that is a rotor inversion axis, and we have 2 rotation axis and a mirror. Then we have 4m, that means a 4 rotation axis and a mirror. Then we have 4 to 2, that means we have 4 times rotation axis and 2 times 2 rotation axis. Then we have 4 over n, that is a 4 times rotation axis with a mirror, and we have just a 4 times rotor inversion axis, and just simply the 4-fold rotation. So then we have here some movies to watch, then we can just figure out how this look like. Here we have just the 4 over m, yeah? That means we have here our crystal, then we have here the a-axis, the c-axis, and the diagonal. So in the typical crystal here, that is the scheelite, and the scheelite, that is a calcium wolframate. So, moment, I will be quickly back. So now I'm back. So that was then the scheelite. So and now we have here the view, we have here from a perspective view, and now we have the rotation about C. So and then it will just rotate here 4 times around C, that is the 4-fold axis, and that is a perpendicular rotation to a mirror plane. So and the mirror plane is this one. Yes, 4-fold rotation axis, that is this one, perpendicular to a mirror plane, and then it will repeat itself 4 times in 360 degrees. Yep, that's all. So, and that means then the 4 over m, yeah? Sometimes you have just 4m, but if you have the 4 over m, then it is perpendicular. The rotation axis is perpendicular to the mirror plane. So, and now we have a rotor inversion, that is the 4 with the bracket on top, and the 2 rotation axis perpendicular to the mirror, that is this 4/2 over m. So, and that is then such a thing. And then we have the total symmetry with photo. So, and that is the chalcopyrite, and that is the Kupfer iron sulfate. So now we are making at first the rotor inversion. That is this 4-fold rotor inversion. Then we are turning it here also around C. So and now if we are talking about the rotor inversion, then we are projecting every point through the center of symmetry to the other side. Yep. So did you get now from Neil this software? Yeah, just try it so that you can run it on your computer or tablet or whatever you have, and then you can just play around. I mean, it's only 3D thinking. So, and now we have the rotation around A1. So, and that is then the 2-fold rotation axis. So, and that is then just here around this axis, and there you have a 2-fold rotation axis. That means it will repeat itself 2 times in 360 degrees. So then now last not least the 4 over m, 2 over m, 2 over m. That is a 4 rotation axis perpendicular to a mirror. Then we have 2 rotation axis perpendicular to a mirror. So then we have here a nice picture, hopefully, yes, and that is the mineral zircon, yeah. And the zircon is a very important mineral when you are dating rocks. Yeah, I told you this before when I showed you my results from Tanzania, and the zircon contains a little bit uranium, and the uranium, the decay from uranium will go to lead, and then you can measure these isotopes, and then you know how old this zircon is. So, and that is such a zircon, a wonderful grown, nice natural sample. So, and here we have then the rotation perspective, then we have the rotation about C. So, and that is then just here along the C-axis, and here we have a fourfold rotation axis perpendicular to the mirror plane. So the fourfold rotation axis is this one, and the mirror plane is this one, yeah? So now we are rotating it, and it repeats itself 4 times in 360 degrees. So now we are making the rotation around A1. So then we have a twofold rotation axis around A1, yeah? So, and we have perpendicular to the mirror plane. The mirror plane is this one. This one was the mirror plane from the 4 times rotation axis. This here is the mirror plane to the perpendicular to the 2 times rotation axis. And now we will check how this look like. Yes, it will repeat itself 2 times in 360 degrees. So, and then we have the rotation about an edge diagonal. There we have now another twofold rotation axis perpendicular to the mirror plane, and the mirror plane is this one. And now let us rotate it. Yep. And that is, yes, and that here is the edge. So I think you got it now how it roughly works with these crystallographic classes. Yeah? So now we are continuing with the hexagonal system. And so in the hexagonal system we have much more possibilities. We have a 3 times roto inversion, then we have 3-2, 3M. Here the 3 times in the roto inversion in combination with the 2 rotation axis and the perpendicular mirror plane. Then we have the 6 over M, we have a 6 times rotation axis perpendicular to the mirror plane. Then we have 6 to 2, that is just a 6 times rotation axis and 2 times rotation axis. So, and then we have the 6 and N, that means we have a 6 rotation axis and 2 mirrors. And we have the 6 over M, 2 over M, 2 over M, that means we have one 6 times rotation axis, 2 times rotation axis, and 3 mirror planes perpendicular to this rotation axis. So in the hexagonal system, we have 3 axes, A1, AB, and A3. They are all called A because they have all the same lengths. Yeah? They have all the same lengths. In the intersection angle is 120 degrees. So, and here C can be different. Yeah? But C is perpendicular to the plane. So you have here, the intersection, you are 120 degrees. So, and here it is perpendicular to C. That means here you have 90 degrees. So then we have here the 3 times rotation axis. That is here the roto inversion. Here we have our crystal, a total symmetry. That is the dioptase. That is also a copper-bearing mineral. These are minerals which you should be able to find here close to Nandi. So, and now we are making the roto inversion. That means that is a threefold rotoinversion axis. So, and then we are projecting all the points from our crystal through the center of the symmetry to the other side. And of course, we can turn the whole thing 3 times. Or it will repeat itself 3 times in 360. So, that was this, or it is still running, yeah? Yeah, that is not that good or not that great with this beamer, yeah, because the beamer has just too less power. But I hope you can see the most important things. And anyway, you have to go by yourself through the CD, and on your own desktop or laptop, you can then you can see it then much better. So you are making at first always the rotation, and after the rotation, you are making the inversion. Yep. Then we have 3-2. That means here we have a nice picture, and that is the quartz here, yeah? So, and then we have the rotation about C, and we have the rotation about A1. So here we have the rotation about C, and there we have a threefold rotation axis, which will repeat itself 3 times in 360 degrees. So, and the same around A1. There we have a twofold rotation axis. So that means it will repeat itself 2 times in 360 degrees. So then we have 3m, and you know it by now, we have we have just a threefold rotation axis, and the m stands for the mirror. So in that or an example for the example here is a tourmaline, and the tourmaline is also a gemstone. And here we have then the rotation about C. So that means we have here just a 3 times rotation axis. Then we have here a 3 times rotor inversion combined with a 2 times rotation axis perpendicular to a mirror. So now we have at first the total, the picture. There we have a rhodochrosite, that is a manganese carbonate. Then we make at first the rotation about A1. There we have a twofold rotation axis perpendicular to a mirror plane. And you know this by now. Here we have the 2 times rotation axis, and the mirror plane, that is just this one. Now we are making the rotor inversion. We have a threefold rotor inversion axis. So and now we are putting just every point again through the center of the symmetry. So you saw it by now. So that was then the three-fold rotation, roto inversion, and the rotation around A1. So that was this. Then we have here 4 over m, and you know it by now. We have then here at first the picture that is an apartheid, yeah? And you know everybody of yours has some apartheids, yeah? These are the teeth, yeah? So the teeth is apartheid, and that is how the apartheid looks like as a crystal. That is a hexagonal prism with a dipyramide. So, and here we have then the rotation about C, that we have here then a 6-fold rotation axis perpendicular to a mirror plane. Then our 6-fold rotation axis around C is indicated here. It's here a term repeat itself here 3 times in 360 degrees, and here is the mirror plane, yeah? And here is the movie. So, and you will see next week a lot of orchids, and these orchid crystals maybe are of this size, 5 to 6 or 7 millimeters, and there you can see the crystallographic phases very, very nicely then in the field. So then we have 6 to 2. You know it by now. Now at first, nice. We have the total symmetry. We have a rotation about C. We have a rotation about 1, and we have a diagonal rotation through the edges. So that is now our 6-fold axis. We'll repeat 6 times in 360 degrees. Yep. Then we have the rotation about A1, that is then in this way. Here we have a 2-fold axis. Will then repeat itself 2 times in 360 degrees. And we have the rotation about the edge diagonal. There we have also a 2-fold rotation axis. Yep. Then we have 6 mm. That means we have, at first we have the total symmetry with photo. So, and then we have the zincite. And we have the rotation about C. That is this one. We have a 6 times rotation axis. And here you have then 2 mirror planes. Here we have a mirror plane, and from this side. And last not least, the more complicated model, the 6 over m, 2 over m, 2 over m. Then we have here perpendicular some mirror planes. And the typical mineral, which from this crystallographic classes, that is the mineral beryl. And I showed you before also some pictures of the beryl. When we were talking about the silicate structures. So here the rotation around C, that is this one, and here we have a 6-fold axis, and here we have perpendicular here the mirror plane. So here the rotation around A1, that is then here, this one, and here we have a 2-fold axis, and here we have the mirror plane perpendicular to it, yeah? And we have the rotation about the diagonal, so that is then here, that is the edge. And here we have again a 2-fold rotation axis perpendicular to a mirror plane. So and now you saw all the crystallographic classes, and I think that should be by now clear how it works. Yeah. So and now we are coming to the Miller indices. So these are these numbers, and I showed you before this one which crops out here, that is the that is the 1, 0, 0. The one which crops out here at the z-axis, that is the 0, 0, 1. So and the one crops out here at the faces from the b-axis, this one, that is the 0, 0, 1, 0. So and here the 1, that means then just here the vector. So that is here the vector 1, and on the A side, then the C vector shows nothing, that means we have here 0, 0, yeah? So and if you are going here to the top, then we have 0, 0, 1, that means C is showing 1, yeah, that is here just the length of 1, yeah? So and the other two are 0 because A is 0 on this side and B is 0 on this side, yeah? So but if we are going here to this edge, yeah, then we have a component from A inside, we have a component from C inside, and we have a component from B inside. And therefore we are writing here on this edge 1, 1, 1. If you are going to this edge on this side, then it is 1, minus 1, minus 1, yeah, because it is here on the negative side, this edge. Here is the A-axis, and here this one, that is the center of the symmetry. Whereas if we are going to this surface, then we have a component from A inside and a component from B inside, but nothing from B inside, then it is 1, 0, 1. So if we are going to this face, then we have a component from A inside, from B inside, but not from C. Then we have 1, 1, 0. If we are checking this face here in the back, then it would be minus 1, minus 1, 0. Did you get this? Just draw a view in your book. Something like this. So that is a cube. So in the center of the symmetry that is inside here, yeah, that is just in the middle. So in this surface here, yes, where this vector A came out, yeah, that is this one, yeah. Maybe this one crops out here, this one crops out here, yeah, something like this. That here is the center of the symmetry. It's actually somewhere here. Yeah, something like this. So that means this vector crops out here exactly in the middle, yeah? On the front surface, yeah? So, and then this one is 1, 0, 0. So this one crops directly out here on this surface, yeah? Then it is 0, 1, 0. And this one crops directly in the middle out of the top surface, yeah? Then it is 0, 0, 1. Yep. So, if this vector here crops out here at the surface in the back, you know, that is the mirror face from this face is also in the back, yeah? Then this is minus 1, 0, 0, yeah? Because it crops out in the back. So if the z-axis crops out here in the back at the bottom here, yeah? Then it's 0, 0, minus 1. Yeah, you have always the positive direction and you have the negative direction, yeah? That is like in your in school, when you had your math class, you have used the Cartesian coordinate system, then it is here plus, here is minus, here is plus, here is minus, yeah? So that's the same for here. If the b-axis crops out here on the negative side, then it is here 0, minus 1, 0. Yeah? So, but if an axis crops out here at the corner, yeah, then you have here at this corner, at this point, you have all three components inside, yeah? So, and therefore we have here 1, 1, 1, yeah? If it is the corner here in the back, then it is minus 1, minus 1, minus 1. And here, I mean, we have just in this example, we have cutted here the edges, and here as well. So if the vector crops out here on this corner, yeah, here on this one, then we have a component from C inside, and we have a component from B inside. That means that is then 0, 1, 1. Is this true? Yes. So, and these are the Miller indices, and with the Miller indices, you can then describe every crystal, yeah? Because you can always move the vector from inside, yeah? So, and this vector can move, is based here on the center of the symmetry, and then you can just move the vector on every face, and then you can describe it with these symbols, yeah? So, and these are the Miller's indices. So, and then we have the Miller-Bravais index. There you are forming then just the intercept. You have here also, for example, here in the hexagonal system, you have A1, A3, A2, and here you have C, and the Miller-Bravais index, you have the not longer 3 numbers as seen in the Miller's indices. You have there then 4 numbers for the hexagonal system, and then you are forming then always, you have here A1 is 1, A2 is 1, but then A3, of course, if you are connecting A1 and A2, A3 is consequently only a half, yeah? and C is also 1. So and then you are forming the intersect, you are just dividing it through, and 1 divided by a minus a half, that is then, using the Wiener-Bravais index, 2 with the minus on the top. So just go through them again by yourself. I mean, it is an easygoing thing. So then we have twinning. Twins you can then see also under the microscope, and we are starting to do the microscopic work in the practical. And for a mineral where you can see every time twins, that is, for example, the plagioclase. So here we have different twins, twinning on an atomic scale. So here we have our atomic structure, and there we have a mirror and a rotation. So let us at first check the mirror, how this looks like. So, and that means you have along here a mirror, and you have along here a mirror. So then we will rotate it. Yeah, that is now not that spectacular. So then we have here the next one, that is contact twinning. So and here we have a mirror plane, and that mirror plane is along 1, 1, 1, and the 1, 1, 1 is where? That is here. That crops then out somewhere here. So and there we have a mineral which is called spinel. And you will also see some spinel crystals then in the field, yeah? Because these metal xenolites in coral, they contain spinel. And if we are lucky, then we are getting a spinel showing this shape. And then you can tell me in the field, where are the twins? So, and here you have then the twin. Again. Yep. So, and that is the spinel twin, and then we have here a polysynthetic twin. Here, for example, this phase is then again 0, 1, 0, because it crops out here, yeah? So, and now we have created twins along 0, 1, 0. Yeah? And these are the twins. So, and these twins, I mean, that is now in an illustration, but it looks like under the microscope exactly like this. So, and then you can have twins along different axes. So, and here these brackets are in such brackets, that is because the twins are that is the movement from the face along 0, 1, 0, yeah? That is then this one. So and if we are putting just the next layer here, then we are running here along 0, 1, 0, yeah? So, and then we are going to the penetration twinning. So that is here, we have here the Karlsbad twin, yeah? The Karlsbad twin, I will also show you then under the microscope. That is the twin which you can find in the K-feldspars, yeah? So in K-feldspar, there is a mineral which you will find in granites, the pinkish one. And that shows the Karlsbad twin. So, and that is a rotation about the 0, 0, 1. Here we have 0, 0, 1. So, and now we are rotating it about around 0, 0, 1, and then you can see the Karlsbad twin. Again. So that is the Karlsbad twin in K-feldspars. Then we have an iron cross twin. That is also here. That is a pyrite, yeah? And that is also here around 0, 0, 1. So, and these are now the twins. So, and then last not least, we have the fluoride twin. That is here along 1, 1, 1. So, and that is here the 1, 1, 1 axis. That means we have a component from a combination of 1, 0, 0, 0, 0, 1 and 0, 1, 0. So, and here you are getting now your twins. Then here something to crystal growth. So I mean what you should know for as an ES203 student, I mean of course you should know the symmetry operation, that is the mirrors and the forward and the rotation axis and the rotor rotation axis. And of course you should know what the twinning is, and maybe you should be able to describe such a cube using the Miller's indices. Yeah, you know we are running on this level. So now we have the growth of crystals. And you know that such crystals are growing, and they are growing always from inside to outside, not the other way around. So, and if they have enough space to grow, then the appearance from outside will reflect the crystallographic symmetry. Yeah? So, but I mean, if they are just crystallizing, or if they do not have any space to grow, then they will not reflect, or the optic will not reflect the internal structure. So then the crystallographic symmetry you can then figure out by using X-ray. But under the microscope, you can see then, or you can observe the crystallographic symmetry using different methods. So here we have a movie showing us how the form changes during crystal growths. So here, for example, we have an octahedron. And now this octahedron started to grow. And then we are making from our octahedron a cube, yeah? So, and here we have the faces from our octahedron. Then it is here, the thing what crops out here is 1, 1, 1. Here we have 1, 0, 1, yeah? Because the B is on the negative side. Then we have here 1, 1, 0, 1, 1, minus 1, because the A is on the negative side. And here we have on the back side here, we have 1, minus 1, minus 1, because here the C is on the negative side as well as the B. That is stage 1. Then we are making stage 2. At stage 2 we are starting here to form a cube, yeah? On the edges, and then we are getting here 0, 0, 1, 0, 1, 0, and 1, 0, 0. Stage 3, it becomes now bigger. So that means our 0, 0, 1 phase becomes bigger. This one as well, and this one as well. And our edge surfaces becomes then smaller and smaller. So now we have very small edge surfaces and bigger cube surfaces. And now we have finally the cube, yeah? So, and now the stereographic projection. That is a little bit complicated. In the stereographic projection, you are putting everything on a stereogram, and therefore you are using the Wolfsche net. So if you are doing the next semester, hopefully with Eleanor the mapping course, then you will plot the thing on the Swiss net. Have you ever? I don't know, we have not done it this one. No. She will do it. So, if you are this mapping crystals, then you are using a stereogram, and that you are putting on such a wolf net. So we have your symmetry axis, we have here a rhomboedron, we have your symmetry axis and mirrors, and then you are putting this on such a wolf net. You must not do this because it is a hell of work. But only that you have heard something about the stereographic projection. So here we have an orthorhombic crystal with three 2 times fold axis, rotation axis over 3 mirrors. So, and now we are putting this orthorhombic crystal in such a spheric, in this ball. So, and then everywhere where the axes are cropping out from all our faces, you will make a point in this sphere, you know where the arrow goes through, yeah? So you have here a crystal. And here you are putting this crystal now in a bubble, yeah? So in a ball. So in all these faces, the arrows here from all these faces will crop out somewhere in this sphere. Yeah? So they will crop out somewhere in this sphere. Let us do it again. Here we have still our orthorhombic crystal. Then we are putting this sphere around. Here we have the equator, if you like, yeah. So and here the arrows from the arrows which are cropping out from the center of symmetry will crop out somewhere on this sphere here, yeah. And here you have north, we have west, we have south, we have east. So and they will just crop out somewhere here, yeah. So, but now you cannot draw in 3 dimensions, yeah. So therefore you have to project then all these points here on the equator, yeah. So in there we have the phase poles. So and now it looks like here, we have now removed the crystal and here our phase poles cropping them out on these spaces in our sphere, yeah? You can put in again the crystal, forming the equator, forming the sphere. Then you have here, these are the lengths, the latitudes on your wool flat. So and then your 1, 0, 0 will outcrop here, the 0, 1, 0 will outcrop here, the 0, 0, 1 will outcrop there. Yes, and at the bottom you have then the 0, 0, minus 1, and here on the backward side you have the minus 1, 0, 0, and here you have the 0, minus 1, 0. So that is this form for these 3 axes, yeah? This one, this one, this one. So and now we are going to the next form. Here we are using then 1, 1, 0, 0, 1, 0, 0, 1, 1. Again the equator, then we are building up the sphere. So and now we have just the arrows cropping out from these surfaces, yeah? So and then you get there your Miller's indices, yeah? Again. Hello. So here again we have then our Miller's indices for these forms. And they are cropping out somewhere here in this sphere. So then we are going to the next forms, to the 1, 1, 1. We are building up again the equator, then the sphere, and now we are projecting these faces here at the corners, yeah? And finally, you got then the Miller's indices for these forms. So and now your ball, on your ball you can see all these points where the arrows cropping out from the different crystal faces, yeah? So and now you have to bring this on a 2D sheet. Now we have here the next one where we have written all phase pools. Then we are putting all together. Again our equator, then we are building up the sphere. So and now all the phase pools are cropping out now. So and then you have described all the faces within this ball, yeah? It looks like something from the Milky Way, but it is not that far away, it's just here everywhere lying around. If you are checking now natural crystals, for example this one, yeah, we have here the quartz again, and you can see all the crystallographic faces here, yeah? And then you are putting your quartz just in such a cloud, and then all this, the arrows perpendicular to your crystal surfaces will crop out somewhere in this sphere. Yeah? Did you get this? So and now we have the phase pools, where we put these phase pools on the equatorial plane. So here we have the picture from before, and there we have now the poles on the northern hemisphere, we have the poles on the southern hemisphere, and we have all the phase pools, and then how it looks like in the 2 over m, 2 over m, and 2 over m symmetry. So here we have now the poles in the northern hemisphere. So and now you can put all the poles here to the south pole, yeah? And then you have projected them on the equatorial plane. Yep, again. You are putting them just all to the south pole, yeah? So, and then you can put all the locations here on the equatorial plane, yeah? And then it looks like this, and here you can number them using then all these Miller's indices, yeah? Now we are doing the same for the poles in the southern hemisphere. We have them here on the southern hemisphere. Now you are projecting them through the equatorial plane to the north pole. And your locations, you can then plot your locations here on the equatorial plane, which looks like this. So, and now we have a combination of all phase poles. That is this. So now you have all phase poles are plotting now on the equatorial plane, and then you have moved all them from 3 dimension into 2 dimension on the sheet of paper. Yeah? So, and now we have the 2m to m to m symmetry. So here we have now plotted all the poles on our paper, and on this paper you have longitudes and latitudes, and then you have here, I mean, 360 degree, and then you can just count it. So, and now you can connect these points. So, and then you get here your 2 times rotation axis, here, 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 and you get here your mirror planes. Could you roughly follow? Just play it around, yeah. By using this software, it's not really complicated. It's just 3D thinking, yeah. Yes, that was this. So, and that you get it, then you get it in the end such a stereogram. Yes, that was this. So, now we have something nice. We have the crystallography and the internal order and structure. So, and here we have mirror planes, and here we have some ducts inside, yeah? Just for a better illustration. So, and we have here a 1-dimensional order, we are talking about 2-dimensional order, and we are talking about 3-dimensional order. So here we have just some definitions. So here we have a lot of ducts, yeah? Here we have the 1-dimensional order, and here we have between these ducts we have a mirror plane. So, and then we can click on the symbols, what happens. So, and here we have just a mirror plane. Here we have a mirror plane, but we are moving it. Here we have actually a roto inversion, and then we have here again a mirror plane inside. So, then we have here the mirror. So they have here a glide line, then the rotation, and the translation. Ah, okay, that is such a thing. That is just, you have to choose the correct answer. So, and a translation is then this one, So in this translation, you are just moving it to this side. So then we have this one. So and now we have to decide what is the correct answer. So and I think that's the mirror. No, that's wrong. Yeah, correct. So and the mirror plane is between here. So then we have this one. So and what do you think is this one? That's the glide line. Yep. You have a mirror and you have a glide line of a half. Yeah. So now we are choosing this one. So and this one is a rotation, yeah? Yes. So you are just rotating like this. So and that is then a 2 times rotation axis, because you can repeat it 2 times in 360 degrees, yeah? One can do this with all the elements, yeah, one must not always use minerals or crystals, you can also use animals, yeah. But with animals it's not that easy because they are usually walking away. So and then we have this one. And here we have a mirror and a rotation. What should I click? Incorrect. 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 Mirror correct, yeah. So and you can then just play around with this stuff. So and now we have the glide line next. No, it should not be the glide, that's a translate. Mirror. Ah, it's this one, yeah. Then we have the 2-dimensional order. Yes, you know these sheets also from the beginning. So we have here generation of 5 2-dimensional nets. Ah, yes, yes, that is just a network. So, and here we have gamma is 90 degrees. So, and that is the angle gamma. And then you will just locate or multiply this net. So, and now we have gamma is not 90 degrees. So that means your unit cell becomes then disaligned. Then we have T1 is T2. I mean here that is the length T1. Here we have T2. So now T1 is T2. Gamma is 90 degree. So then you will form such a thing, and if we have here gamma is 90 degree and T1 is and T2 is the same, then we are sitting in which crystallographic or which crystallographic symmetry does this reflect? That is tetragonal or cubic, yeah? So now we are doing the next for gamma is 60 or 120 degree, then we should know by now which crystallographic system does this reflect. That is hexagonal. So then we have here our hexagonal shape. You can easily see it now, yeah? And here you have the angle of 120 degree, and T1 is T2. Okay, that was this one. So, and then gamma is not 90 degree, not 60 degree, and not 120. Then it's maybe something tricky. So, and therefore you are running here, you are dealing here with mirrors, you are running on glide planes, and you are running on translocations, and you are running on rotations, yeah? That is how these four operations you can use to build up your symmetric model, yeah? And this is can all reflected by using the 6 crystallographic classes. So, and then we have that was the generation of 5 two-dimensional nets. So, and then we have the generation of 7 plane groups. Here we have different plane groups. So, and that is just the net type, and here we are dealing, T1 is not T2, that means we have here 2 different lengths. Then we have, the angles are not 60 degree, not 90, or not 120. So then the next one, that is the superimposed motif. So in the superimposed on the oblique net, that is here a twofold rotation axis perpendicular to the screen. So this is the symbol for a twofold rotation axis. That means you can move this 2 times in the 360 degree. Yeah? So then we have the motif of symmetry elements. Yeah. And here between you have everywhere your twofold rotation axis. So, and that is then the symmetry content, and that is just a twofold rotation axis. Then we are going to this one. So here the net type again. But compared to before, we have here the situation that we have T1 is T2. But the angles are not 60, not 90, and also not 120 degrees. So, and here we have again the mirror operation, or not the mirror operation, we have here also a 2 times rotation axis here. So, but compared to the thing before, we have now here also a mirror, yeah? Here we have a mirror, and here we have a mirror, here we have always, these red lines are marking here the mirrors. So before we had only a twofold rotation axis, and here we have the mirror, because the axis T1 and T2 is the same. So, and these are here, we have here the mirror and glide. Here we have the situation that T1 is not the same like T2, but the angle gamma between is 90 degrees. So then we have here again a 2 times rotation axis. And the mirror as well. Yep. So here net type, we have again 90 degrees, and we have the situation that the arrow T1 has the same length like as the arrow T2, and then we are sitting somewhere, you can see it by now. What are you thinking, what type of rotation axis you are getting? How often can you repeat this square in 360 degrees? Yes, 4 times. So then it means we are sitting here in the tetragonal system. Yeah? So, and if you are looking this, how many mirror planes you will get only on the surface? Yes, you get at least now 2. That is just, this point can be reflected on this side, this point can reflect it on this side. Yeah? You have here a mirror, you have here a mirror. So, and of course, perpendicular, you have also a mirror. Yeah? So here we have it, here is the fourfold axis, yeah? So, and here you have your symmetry elements, yeah? You have then here a fourfold axis, here you have a fourfold, here, 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 and between you have twofold axis, yeah? So, and that is then just P4. So you have the location of a fourfold and twofold axis. Because only T1 and T2 has the same length, yeah? That means T3, which is popping out here, is different in length, and therefore you have here on these surfaces only a twofold axis, yeah? That looks then like this. So, yeah. So that means this here is T1, this here is T2, and T1 is T2, but it is not the same length as T3. Therefore, you are getting on this side, for this axis which is scoping out here, you are getting the 4 times rotation axis, yeah? But on this side, you are getting just a 2 times rotation axis. Because T3 has another length, yeah? You got it, yeah? It's not that complicated. So, and of course, then you can put in also everywhere the mirrors. Just play this CD by yourself a few times through, then you must have it. That is not a big issue here. So, and that we already had, yeah. Let us just check. Ah, yes, yes. No, here they made a double twerk. We have here the same situation, T1 is T2, gamma is 90 degrees, but here they put then also the mirrors inside. We have here 4 mirrors, yeah? But we have already discussed it. So, and now you have everywhere the mirrors inside as well, yeah? So that was this, and that was this. Now we have the 3-dimension order. Yes, I think with this we can continue tomorrow.